Are you ready for tonight? Relax your body and immerse yourself in the vast unfolding story of the cosmos. At this very moment, you are perched on a rocky world racing through space at 670000 miles per hour. That world circles a blazing nuclear engine about 1 million times larger than it. And that star is only one among 400 billion stars, drifting and rotating within a galaxy so immense that even light needs 1,000,000 years to get from one side to the other. Yet the truly unsettling thought is this: our whole galaxy, with its billions of planets and all the civilizations that might exist, is little more than a single grain of sand in an ocean containing 2 trillion other grains. Imagine you are standing in the heart of New York City at midnight. The lights spill outward in every direction, street after street, until the buildings dissolve into darkness at the horizon. Now extend that glowing sprawl beyond the next state, all the way across the entire continental United States. Then push it onward across the Pacific Ocean to Asia. Keep going, wrapping it around the whole Earth. And then take that entire distance and multiply it by 6 billion. You have just built an intuition, as best you can, for the width of our galaxy. With careful measurement, scientists have confirmed that the Milky Way spans 1,000,000 light years from edge to edge. 1 light year is 6 trillion miles. So our galactic home stretches 6,000,000 trillion miles across. To write that number in full, you would need a string of zeros long enough to run from your home to the nearest grocery store. And here comes the first blow to common sense. Even with this mind-crushing scale, the Milky Way is only the opening rung of a cosmic ladder rising toward magnitudes our brains simply did not evolve to handle. Every pinpoint of light you see glittering in the night sky belongs to our own neighborhood. That pale, hazy band arcing across truly dark skies is the side-on view through our spiral arms. We are inside this vast, stellar city, embedded within it, the way a single cell sits inside a living creature. From our position, roughly 2,600,000 light years from the galactic center, we can watch regions where stars are being born, where new suns flare into existence. Year after year, we observe stellar nurseries where gravity gathers cold gas and dust, compressing it until it ignites into a burning sphere. We see ancient red giants reaching the end of their lives, some dying in spectacular explosions that scatter heavy elements into space. Everything you have ever touched, the atoms in your body, the calcium in your bones, the iron in your blood, is bound up with this ongoing galactic story. All of this unfolds within our local theatre of the Milky Way. But the aspect that truly disturbs the imagination is not only the size it is, what that size points toward, because the Milky Way is just one member of a hierarchy of structures that becomes ever larger and ever harder to picture. Each new level of organization dwarfs the one below it, by factors so extreme that ordinary human experience stops being a useful guide. To stand on Earth and contemplate galactic distances is like asking an ant to understand the size of North America. The ant might sense that something enormous lies beyond its tiny patch of ground, but it has no mental machinery for continents. We face an equivalent limitation when we confront the cosmos. Our brains were shaped for life on African plains, for judging the distance to water, to shelter, to prey. They are not built for distances measured in light years, nor for timescales that laugh at a human lifetime. That gap between what the universe is and what our intuition expects becomes one of the first clues that reality operates on levels far beyond the familiar. And every time we climb higher, each new structure, we discover demands that we loosen our grip on an earthbound perspective and accept scales that feel almost like pure mathematics rather than physical space. The ancient Greeks imagined the stars as small holes in a celestial sphere wrapped around the Earth. Today we know that even our own galaxy contains mysteries that would have overwhelmed their boldest speculation. With every telescope that looks deeper, we uncover further layers of cosmic architecture, extending outward toward horizons we can barely perceive. And yet, compared with what lies beyond the Milky Way, begins to resemble a single room in a vast cosmic mansion, a mansion with more floors than the mind can comfortably hold. Now consider the role of light, the fastest thing we know. Nothing in the universe can outrun a photon crossing the vacuum of space. Moving at 670 million miles per hour, light can circle the Earth 7 times in a single second. That speed sets the ultimate limit for sending information and for traveling through space. And still, even light needs 1,000,000 years to traverse our galaxy from edge to edge. Pause and let that settle. The light leaving some distant stars in the Milky Way tonight began its journey when early humans first learned to make fire. Photons arriving here from the far side of the galaxy set out long before written language existed. They have been carrying news of distant stellar events since a time when our ancestors were only beginning to cultivate the land. Astronomers turn this travel time into a cosmic measuring stick. When we look toward remote regions of our galaxy, we are not seeing them as they are now, but as they were thousands of years ago. The Milky Way you see in the sky tonight is a mosaic made from many different moments in time. The nearest stars show us comparatively recent history. The more distant ones reveal an older chapter of the same unfolding story. Distant stellar neighborhoods whisper of an ancient story. We never observe our galaxy as it exists in this precise moment, but as a blended record stretched across thousands of years. This separation in time gives rise to one of the most extraordinary confirmed truths in astronomy. Every image of our galaxy captures many eras at once. Light from different regions began its journey toward us at vastly different moments in history. To look at the Milky Way is to gaze backward through time over a span far exceeding the length of human civilization. The idea becomes even more astonishing when we account for galactic rotation. Our galaxy turns like a vast cosmic pinwheel. The solar system completes a single orbit around the galactic center once every 200 million years. While light crosses the breadth of the Milky Way, the galaxy itself turns through nearly half a rotation. Its structure subtly reshapes even as its light is still in transit. The implications for communication across the galaxy are deeply unsettling. Any signal sent from one side to the other encounters an unavoidable limit. Radio waves and laser beams travel at the speed of light. This means galactic communication demands patience, measured not in lifetimes, but in geological epoch. If a civilization on the far side of the Milky Way transmitted a message today, our great-great-grandchildren would not live to see its arrival. This constraint ensures that the galaxy can never operate as a single coordinated system. Its regions remain fundamentally disconnected, separated by the ultimate speed limit of information. What seems like one grand cosmic entity is in fact a collection of isolated zones, each evolving without awareness of distant stellar districts. The ancient photons reaching us tonight bring news from a galactic past that can be studied but never revisited. Every star we observe reveals conditions that existed long before our species learned to raise its eyes to the night sky. And yet this challenge of communication is only the smallest difficulty we encounter when confronting cosmic distance. Step outside beneath a clear sky and find the brightest star overhead. That brilliant point is Sirius, shining 25 times brighter than our Sunday. Its prominence was so striking that ancient cultures anchored their calendars to its motion. To human vision, Sirius appears close enough to touch, as though a tall ladder might reach it. Reality dissolves that illusion instantly. Sirius lies between 8.6 and 10 light years from Earth. That span corresponds to 51 trillion miles. Driving a car at typical highway speed toward this star would take 300 million years. You would need to maintain 65 miles per hour without pause, since long before complex life emerged on Earth. Yet Sirius is practically a neighbor by galactic standards. Most stars in the Milky Way are separated by distances so immense they resist intuitive understanding. On average, neighboring stars are 4 light years apart. In cosmic language, this is an almost flawless vacuum, dotted with rare tiny islands of matter. To picture this emptiness, imagine shrinking our solar system until the sun is the size of a basketball. At that scale, Earth becomes a grain of sand, circling 26 feet away. The nearest star would be another basketball placed in an entirely different city, perhaps Denver if you began in New York. Between those basketballs lies almost nothing at all. This vast emptiness carries profound consequences for interstellar travel. Even moving at the speed of light, reaching nearby stars, requires years. Spacecraft built with conceivable technology would need tens of thousands of years to reach even the closest stellar neighbors. Most of our galaxy will remain forever beyond the reach of human exploration. The immense void between stars also clarifies why contact with alien civilizations appears so improbable despite the abundance of possible worlds. If intelligent beings exist around distant stars, they confront the same barriers of space and time that confine us. The universe itself seems arranged to keep thinking species apart, separated by distances too great for meaningful exchange. Astronomers estimate that the Milky Way contains around 400 billion stars, yet these countless suns are scattered so thinly that each lives in near total isolation. The night sky deceives us, making stars appear densely packed, when in truth they inhabit a realm defined by vast and enduring cosmic solitude. Across the vast expanse of our galactic neighborhood, solitude reigns supreme. Even within the crowded heart of the Milky Way, where stars gather in tighter formations than in our own spiral arm, immense voids still stretch between one sun and the next. What we perceive through telescopes as a brilliant sea of lights is in truth a structure built mostly from emptiness. To gaze upon these great voids is to glimpse the true design of the cosmos itself. Matter, that precious rarity, drifts through an almost infinite ocean of nothing. We inhabit one of these small islands of substance, a fragile speck suspended in the dark. And yet, compared to the unfathomable distances between galaxies, even this galactic emptiness feels almost crowded. Picture for a moment counting every single star in our galaxy. Start with the sun, then move outward through the spiraling arms. Count every red dwarf, every blue giant, every twin star locked in a graceful gravitational dance. If you kept a steady rhythm of 1 star per second, without rest or nourishment, you would still be counting after 12,600 years. Astronomical observations show that our Milky Way harbors somewhere between 100 billion and 400 billion stars. We cannot yet know the precise number, for thick clouds of interstellar dust obscure our view of the farthest reaches. Hidden within dark nebulae lie stars, detectable only in the infrared. Even the lower estimate, 100 billion suns, is almost beyond the grasp of imagination. Every single one of these stars is a furnace of nuclear fusion, transmuting 4 million tons of matter into radiant energy every second. Multiply that by hundreds of billions of stars, each performing this alchemy simultaneously, and the energy output of our galaxy surpasses human comprehension, numbers so immense they must be written in scientific notation. Yet for all its blazing splendor, this galactic multitude represents but a faint whisper in the cosmic chorus. The Milky Way, despite containing enough stars to power quadrillions of civilizations, is merely a middling spiral among countless others. Some galaxies boast more than 1 trillion suns. Others, the dwarfs, cradle only a few billion. The mathematics of probability tells us something even more extraordinary. If just 1% of all these stars host Earth-like planets, then our galaxy alone could hold billions of worlds capable of sustaining life. Some may cradle ancient civilizations far older and wiser than our own. Others may teem with forms of existence so different that no human language could describe them. And yet even all of this, the stars, the planets, the civilizations, is insignificant on the scale of the observable universe. Together, they account for less than 1% of all matter that exists. Our entire galaxy, with its billions of suns and planets, is no more than a single grain of sand scattered across an endless cosmic shore. This realization upends every notion of human centrality. The ancient belief that Earth stood at the heart of creation now feels almost charming in its innocence. We live on a small planet orbiting an ordinary star, one among hundreds of billions, inside a galaxy that is utterly typical among trillions. Those 400 billion stars burn with energies that dwarf anything found on Earth. Their collective light forms the glowing band we call the Milky Way, arching gracefully across the night. Their gravity sculpts the spiral arms guiding the birth of new stars. Their deaths seed the universe with the heavy elements from which planets, oceans, and life itself are made. All this wonder unfolds within what we call our galactic neighborhood. But even this is just the beginning. Look toward the constellation of Andromeda on a clear autumn night. That faint blur of light, so small it might escape, notice was once thought to be a mere cloud within our own galaxy. Now we know the truth. It is another galaxy, entirely containing more than 1 trillion stars and spanning 220,000 light-years over twice the diameter of the Milky Way. To contemplate that faint smudge is to stand at the edge of understanding, gazing into the infinite. This vast galactic colossus holds within it enough stellar furnaces to outshine the Milky Way by a factor of 3 or even 4. If we imagine our galaxy as New York City, then Andromeda would stretch across the entire eastern coastline of the United States. Yet confirmed measurements reveal something even more astonishing. Andromeda is hurtling toward us at 250,000 miles per hour. This celestial convergence will eventually give rise to the most magnificent spectacle our solar system will ever encounter. Computer models show that in 4.5 billion years, these two immense spiral galaxies will meet, entwining in a gravitational ballet that will unfold over several billion years. The result will be the transformation of both systems into a single elegant elliptical galaxy already nicknamed Milky by astronomers. During this monumental event, our solar system will probably endure unscathed. The enormous emptiness between individual stars ensures that direct collisions remain exceedingly rare, even when galaxies collide. Instead, gravity will redirect the Sun and its planets into new paths around the shared galactic core. Earth may find itself cast into the distant reaches of the merged galaxy, beneath skies filled with unfamiliar constellations. But what truly bends the mind about Andromeda is not its immense size, nor its impending union with us. It is what it reveals about the nature of distance and time. The light you see from Andromeda tonight began its journey 2.5 million years ago, when those ancient photons first set out toward Earth. Our distant ancestors were just discovering how to shape stone into tools. The galaxy we gaze upon existed long before modern humans walked the planet. Because of this cosmic delay, we can never see Andromeda as it is now. We witness its ancient self, preserved in light that has crossed the cosmic abyss for millions of years. The galaxy currently rushing toward us may appear utterly different from the one we observe through our telescopes. Even more profound is what Andromeda teaches us about the vastness of space. Though it is our nearest major galactic companion, the distance is so immense that light itself takes millions of years to travel between us. This represents the smallest step beyond our own galactic frontier, a void separating the Milky Way and Andromeda, filled with almost nothing but wisps of gas and the mysterious presence of dark matter. This intergalactic wilderness hovers near absolute zero, with a density lower than any vacuum humans could ever create. Yet this emptiness is alive with unseen forces that orchestrate the grand movements of galaxies across eons. The eventual union of our galaxy with Andromeda will ignite a blaze of light visible across far-off cosmic neighborhoods. And even this grand collision is but a local performance in a far greater gravitational symphony. Our Milky Way drifts, not in isolation, but as part of a vast collective known as the Local Group, a gravitational family of more than 50 galaxies bound in an endless cosmic waltz. This galactic community stretches roughly 10 million light-years and possesses enough mass to warp space and time across unimaginable expanses. Observations show that most members of this group are dwarf galaxies, each home to only a few billion stars. These smaller companions orbit the two great spirals, our Milky Way and the oncoming Andromeda, much like planets circling a binary star. Among the most notable of these companions are the large and small Magellanic Clouds, visible to the naked eye from from the southern hemisphere. These irregular galaxies orbit the Milky Way at distances of 160,000 and 200,000 light-years. Their closeness provides astronomers with living laboratories to study galactic interaction in motion. Evidence shows that the Milky Way is actively consuming its smaller companions. The immense gravity of our galaxy pulls streams of stars and gas from the Magellanic Clouds, feeding material into the galactic disk. This process of cosmic nourishment has unfolded over billions of years, gradually enlarging the Milky Way as it absorbs nearby dwarf systems. Yet this act of galactic consumption reveals something deeper about the evolution of the cosmos. Galaxies are not isolated islands adrift in nothingness. They are members of vast gravitational societies, their destinies shaped through constant interaction and exchange across the grand architecture of the universe. The night sky may seem tranquil, but every star and galaxy tells a story of immense violence unfolding over cosmic ages. Our local group of galaxies drifts together through space, moving as a single graceful entity. The entire galactic neighborhood, including the Milky Way, is journeying toward the Virgo cluster at a speed of about 400 meters per second. This immense motion carries our region of galaxies across distances so vast that even the largest galaxies become insignificant. We are travelers aboard a cosmic ship, gliding silently through the intergalactic ocean toward gravitational havens we can scarcely imagine. Yet there is something even more astonishing. The galaxies of our local group are enveloped by halos of dark matter, stretching far beyond the edges we can see. These invisible structures contain roughly 10 times the mass of all the stars and gas combined, forming the unseen framework that binds galaxies together. Dark matter is the gravitational glue shaping the universe on scales we can only begin to comprehend. Even though the fabric of space itself expands, the galaxies within our local group still obey precise mathematical laws of motion. Each one follows a vast elliptical orbit, approaching and retreating from its companions over cycles lasting billions of years. These gravitational encounters ignite new stars, twist galactic arms, and scatter matter across intergalactic space. To grasp this cosmic choreography, we must think on timescales that stretch beyond human comprehension. What we see today is but a fleeting frame in a story lasting tens of billions of years. Galaxies merge and part in an endless waltz too slow for the human eye, yet their motions preserve the record of that ancient dance. And this local ballet is only the beginning. It forms the smallest unit in a grand hierarchy of structure. Galaxy clusters are the universe's most massive bound systems, immense cosmic cities containing thousands of galaxies. Their collective gravity bends the very geometry of space across distances of millions of light years. The nearest of these colossal gatherings, the Virgo cluster, lies some 54 million light years away and contains more than 300 galaxies. When astronomers calculated its gravitational strength, they discovered something puzzling the visible matter. All the stars and gas could not account for the binding force holding it together. Within these clusters, galaxies speed through space at nearly 3 million miles per hour. Such velocities should have torn the clusters apart long ago. The resolution of this mystery came with the realization that most of the mass is invisible. Dark matter outweighs all luminous material by about 10 to 1, providing the deep gravitational wells that prevent the clusters from flying apart. We know of this mysterious substance only through its influence on light and gravity. By observing how massive clusters warp space itself, astronomers use gravitational lensing to map dark matter. These clusters bend light so dramatically that they magnify and distort distant galaxies behind them, acting as natural telescopes written into the fabric of the cosmos. The extent of this distortion reveals how much unseen mass is present. Repeated measurements confirm that dark matter dominates the mass of clusters, though no instrument on Earth has yet detected it directly. One of the most striking proofs comes from the Bullet cluster, where two immense clusters collided at speeds exceeding 10 million miles per hour. The glowing gas clouds slowed and collided, but the dark matter components sailed straight through unaffected. The separation between visible and invisible matter spanning millions of light years stands as undeniable evidence of dark matter's independent existence. Galaxy clusters are also laboratories of the extreme. The gas between their galaxies is heated to around 100 million degrees, stripping electrons from atoms and creating plasma that shines in X-ray light. This hot material contains more mass than all the galaxies combined, yet remains invisible to ordinary telescopes. The intergalactic space within these clusters teems with particles accelerated to nearly the speed of light by magnetic fields stretching for millions of light years. These cosmic rays emit radio waves, tracing magnetic bridges that link distant galaxies together. Ultimately, galaxy clusters reveal the grand architecture of cosmic evolution. They mark the endpoints of gravitational collapse, the places where matter has pooled over billions of years. From the earliest moments after the Big Bang, dark matter began to gather, creating wells in the fabric of space into which galaxies fell. Over cosmic time, those galaxies merged and coalesced into ever larger clusters, the great fortresses of structure in our universe. The colossal galaxy cluster known as El Gordo holds the mass equivalent to 3 quadrillion suns and stretches across 15 million light years. This cosmic titan resides 7 billion light years away, so we see it as it was when our solar system was still in its infancy. Galaxy clusters like this one form the knots of an immense cosmic framework that resembles a three-dimensional web woven through the universe. Superclusters are the grandest confirmed gravitational formations known. They reach across such extraordinary expanses that even light takes hundreds of millions of years to cross them. Our own local group is part of the Laniakea supercluster, a vast gravitational domain spanning 500 million light years and encompassing more than 100,000 galaxies. The realization that galaxies gather into superclusters reshaped our view of the cosmos. Rather than existing in random isolation, galaxies form intricate networks connected by filaments of dark matter and streams of gas. These immense bridges of matter link clusters across unimaginable distances, creating a hierarchy that defines the universe's largest architecture. To map our local supercluster, scientists track the subtle peculiar motions of thousands of galaxies. Although cosmic expansion drives galaxies apart, gravity pulls the nearby ones toward denser regions. By charting these gravitational flows, astronomers discovered that the Milky Way and countless neighboring galaxies are drifting together toward a colossal region of attraction. This gravitational anchor, known as the Great Attractor, contains the mass of tens of thousands of galaxies hidden behind dense clouds of interstellar dust within our own galactic plane. Its immense pull shapes the movement of galaxies over hundreds of millions of light years, drawing entire clusters along the invisible filaments of the cosmic web toward greater concentrations of matter. Yet the Great Attractor itself is only a single thread within a still grander tapestry. New observations reveal that Laniakea belongs to a titanic complex of superclusters stretching over 1 billion light years. This assembly, the Pisces-Cetus supercluster complex, may be the most extensive coherent structure ever observed in the cosmos. Such colossal formations challenge our understanding of cosmic evolution. They emerged through gravitational processes unfolding across billions of years, sculpting the patterns we see today. When the universe was less than 1% of its present age, dark matter began to clump together, forming the scaffolding upon which visible matter would later arrange itself. Defining the exact boundaries of a supercluster is difficult because they gradually merge into one another. Unlike the tightly bound galaxy, superclusters are loosely connected, and many regions may already be dispersing under the influence of cosmic expansion. Some areas continue collapsing under their own gravity, while others are stretched apart by the mysterious force of dark energy. The geometry of these immense formations resembles living tissue more than simple geometry. Laniakea appears like a vast sheet with filaments branching outward, much like the neural pathways of the human brain. Perhaps this resemblance is no accident. Both systems grow through natural processes that produce branching hierarchical networks. To observe such cosmic architecture, astronomers employ telescopes capable of mapping millions of galaxies across unfathomable distances. The Sloan Digital Sky Survey has produced three-dimensional maps that reveal superclusters, by precisely measuring distances to over 1 million galaxies. These surveys show that superclusters connect to form a vast lattice, a kind of cosmic scaffolding that extends through the observable universe. When mapped in detail, this cosmic web resembles a pattern of soap bubbles suspended in space, with galaxies clustering along the bubble walls and enormous voids occupying the interiors. Step back far enough, and the universe reveals an astonishing, almost organic pattern. Galaxies are not scattered at random. They trace the threads of an immense, three-dimensional web, a froth of cosmic foam suspended in darkness. This structure, the cosmic web, is the grandest manifestation of order in the universe. Simulations confirm that it arose naturally through the slow choreography of gravity, beginning shortly after the Big Bang. Dark matter began to gather when the universe was just a few 100,000 years old, planting the gravitational seeds that would one day grow into the cosmic framework we see today. The web itself consists of 4 interwoven elements spanning billions of light years, with dense nodes marking the intersections where galaxy clusters take shape. Filaments span the cosmos like vast celestial highways, guiding streams of matter across unimaginable distances. At their intersections, immense walls arise, forming sheet-like plains where galaxies gather. Between these luminous structures lie the cosmic voids, regions of near-perfect emptiness. Scientists have charted this intricate architecture by observing millions of galaxies and measuring their three-dimensional coordinates within the expanding universe. These grand surveys reveal a universe sculpted into immense bubbles, their boundaries traced by galaxies, their interiors filled with emptiness. The result is a foamy lattice stretching uniformly across the observable cosmos. The sheer scale of these patterns defies comprehension. Each filament can reach hundreds of millions of light years in length, yet remains no more than 20 million light years thick. From a universal perspective, these threads appear impossibly slender, but within them lies enough material to form billions of galaxies. Matter flows through them as water flows through channels, feeding the birthplaces of stars and worlds. Where filaments converge, colossal galaxy clusters emerge, gravitational hubs that capture matter for billions of years. These intersections are the universe's bustling metropolises where galaxies collide, stars ignite, and supermassive black holes grow. The most massive clusters define the densest nodes of the cosmic web. Yet what renders this structure so extraordinary is its restlessness. It continues to evolve as the universe expands, and dark energy accelerates the drift between distant realms. Eventually, filaments connecting far-off superclusters will tear apart as cosmic expansion overwhelms gravity's grasp. The gas within these threads remains invisible to ordinary telescopes, glowing faintly instead in ultraviolet and X-ray light. This intergalactic medium holds more mass than all the stars combined, though it is spread so thin that a cubic meter may contain just a few atoms. Recent detections have confirmed the presence of the warm, hot, intergalactic medium gas within filaments heated to millions of degrees, but with densities barely higher than the cosmic vacuum. Finding it required specialized X-ray instruments capable of sensing its faintest whispers of radiation. The cosmic web likely extends far beyond what we can observe, suggesting that our maps capture only a fraction of the universe's hidden design. Within its structure lie voids so empty they stretch the limits of imagination. Picture a sphere 300 million light years across, almost completely devoid of galaxies. No stars burn there, no planets orbit, only silent darkness fills its span. One of the largest, the Bootes void, discovered in 1977, measures about 330 million light years across, yet contains fewer than 60 known galaxies. If our own galactic neighborhood were inside it, the nearest major galaxy would appear only as a faint blur in the most powerful telescope. Observations confirm that voids occupy roughly 80% of the universe's volume. These vast expanses separate the filaments where galaxies cluster, yet their matter content falls below 15% of the cosmic average. Early cosmologists were baffled by their existence, once proposing that immense explosions cleared such regions. Now we know they arose naturally as matter flowed into denser zones, leaving emptiness behind. Within these voids, temperatures linger just above absolute zero. Densities drop so drastically that hydrogen atoms may be spaced miles apart. This near-perfect vacuum rivals the emptiest chambers physicists can produce on Earth. Still, voids are not entirely empty. Invisible dark matter forms subtle frameworks connecting them to the surrounding web. Simulations show even within voids, delicate filaments of dark matter persist too insubstantial to trap ordinary matter. These ghostly strands weave a web within the web-extending structure into apparent nothingness. The few galaxies that inhabit these realms evolve differently from those in crowded clusters. They are smaller, bluer, and alive with star formation. Their solitude shields them from disruptive gravitational encounters, allowing them to shine as quiet witnesses to the vast and silent beauty of the cosmic web. The vast expanse known as the Giant Void, or the Canes Veneticus supervoid, stretches nearly 1.8 billion light-years across. It is a cosmic desert, so empty that if our Milky Way had formed at its heart, we might not have discovered the existence of other galaxies until the 1960s. The night sky would be almost completely dark, save for a few faint local neighbours glimmering at the edge of perception. These cosmic voids leave their signature on the ancient radiation that still echoes from the Big Bang. Photons travelling through these immense empty regions experience slightly altered gravitational pulls compared to those moving through denser cosmic webs. These minute temperature shifts in the cosmic microwave background allow us to trace the shapes and positions of voids across the universe. Over billions of years, as space itself expands, these vast empty realms grow larger while the matter around them continues to collapse toward the surrounding cosmic structures. Yet even these colossal voids appear small when set beside the largest solid forms in existence. The most enormous structures we have ever found stretch across distances so immense they test the very boundaries of what our physical laws should permit. These are immense walls and sheets of galaxies billions of light years wide, yet only about 20 million light years thick, delicate filamentary membranes suspended in the darkness. The first of these discovered was the Coma Wall, a structure extending 500 million light years in length, but only 16 million light years in thickness. It holds thousands of galaxies arranged in a vast thin sheet that, if viewed from the side, would appear as a nearly invisible line against the void. Located roughly 300 million light years from our local group, it is one of the grand features of our cosmic vicinity. But since its discovery, astronomers have uncovered far greater structures, pushing the limits of what theory predicts. The Sloan Great Wall, spanning 1.3 billion light years, stands among the largest known objects in the cosmos. This immense barrier of hundreds of thousands of galaxies forms a pattern that stretches across about 1% of the diameter of the observable universe. Even more astonishing is the Hercules Corona Borealis Great Wall, revealed by tracing the origins of distant gamma-ray bursts. It spans an almost unimaginable 10 billion light years, so vast that light itself, travelling at its ultimate speed, would need more than 1/10 of the universe's age to cross from one side to the other. The existence of something so immense strains the limits of our models for how structure in the universe should arise. These walls appear where the filaments of the cosmic web meet and intertwine across inconceivable scales. Computer simulations show that dark matter naturally weaves these great sheets as gravity pulls matter inward from multiple directions. Ordinary matter follows this hidden framework, forming the galaxies that we can see. The delicate thinness of these cosmic walls has real consequences. It shapes how galaxies evolve across distances that defy comprehension. Galaxies bound within these walls feel intense tidal forces. They can be drawn into bursts of star formation or stripped of their outer layers by nearby giants. The gravitational environment here is entirely different from that of the voids or dense clusters, giving astronomers a natural laboratory for studying the growth of structure on the grandest scales. The specific arrangement of galaxies within these walls holds clues to the earliest conditions of the universe, only moments after the Big Bang. Comparing these observations with our simulations allows scientists to test their ideas about dark matter and cosmic evolution. Yet perhaps the most astonishing realization is that even these vast walls are only middleweights in the architecture of existence. They are intermediate structures, bridges between superclusters and the largest detectable frameworks of galaxies. They form the building blocks of an even greater cosmic order, stretching to the very edge of what we can observe. Their discovery reminds us that the universe is not static. These monumental structures are still changing, pulled and stretched as cosmic expansion continues. One day, dark energy will tear them apart, overcoming the gravity that now binds their galaxies together. And perhaps beyond our current horizon, there are still larger walls, connected structures, extending into regions we cannot yet see. The very thought hints that the universe may be woven into an order grander than we can ever imagine. Aim the most powerful telescope toward what seems to be an empty patch of sky. Let it gather light for days, and you will find that even the darkness is filled with the faint whisper of eternity. The resulting image unveils something that should profoundly transform the way you perceive existence itself. Within that minuscule region, no larger than a single grain of sand held at arm's length, lie thousands of galaxies. The Hubble Ultra Deep Field, assembled from 800 separate images over 11 days of continuous exposure, revealed more than 10,000 galaxies within a portion of the sky that spans only 13 millionths of the celestial sphere. Each one of these galaxies is home to billions of stars, many of which may host planets where life could have emerged. Through careful analysis of these deep field observations, astronomers have been able to estimate the total number of galaxies in the observable universe. The latest results, drawn from both the Hubble and James Webb Space Telescopes, suggest that 2 trillion galaxies inhabit the cosmic volume accessible to our instruments. 2 trillion is a number so vast that it surpasses human understanding. Even if you were to observe one galaxy every second without pause, it would take you 63,000 years to see them all. Written out in full, that number carries 13 zeros, 2 million galaxies scattered across the observable universe. Each of these cosmic islands contains its own stellar population. Conservative calculations indicate that an average galaxy contains about 100 billion stars. When multiplied by the estimated number of galaxies, this produces a stellar census, exceeding 10 to the 24th power individual stars, far more numerous than all the grains of sand on every beach on Earth. Yet what makes this realization so unsettling is the way it shifts our sense of importance within the cosmic order. Our entire local group, a collection of more than 50 galaxies, accounts for less than 150th billionth of the total population. The Milky Way, with its 400 billion stars, is not exceptional at all. It is merely one ordinary galaxy among 2 trillion companions sharing the same cosmic ocean. Recent evidence suggests that even these estimates may fall short. With each technological advance, astronomers uncover faint dwarf galaxies previously hidden from view, tiny systems containing only millions of stars that may outnumber the grand spirals by 10 to 1. The deep fields also reveal galaxies at various stages of their evolution. The most distant appear as they were billions of years ago, when the universe was young and the rate of star formation was far greater than it is today. These ancient structures differ markedly from the mature galaxies we observe nearby, offering direct insight into the universe's history. Across the vastness of space, galaxies form an immense web-like structure stretching to the limits of observation. No matter which direction astronomers look, the distribution remains broadly consistent, confirming that on the largest scales, the universe appears uniform. This remarkable regularity tells us that our observable region provides a fair sample of the cosmos as a whole. Yet each deeper survey extends our reach, revealing galaxies once hidden beyond previous limits. Every improvement in telescope sensitivity adds billions more to the cosmic register. The 2 trillion galaxies we know of today might represent only a small fraction of all that exist. Walk along a shoreline and lift a handful of sand, Count the tiny grains between your fingers. In that handful, there are roughly 10,000 particles, each one a fragment carved by millions of years of wind, water, and time. Now expand that image to include every beach across the globe, the Caribbean, the Mediterranean, the Pacific atolls, the frozen Arctic coasts. Add every grain of sand on every beach of every continent and island. Scientists estimate that Earth's shores contain around 7 quintillion grains of sand. Written as a number, it stretches across 20 digits, 7 million particles. And yet even that staggering count of sand is dwarfed by the number of stars. The observable universe holds far more stars than there are grains of sand on our planet. Those 2 trillion galaxies harbour stellar furnaces that outnumber Earth's sand grains by thousands to 1. Every time you hold a handful of sand, remember that for each grain resting in your palm, there are thousands of suns burning across the universe. And when we consider how many planets orbit those suns, the comparison becomes almost beyond imagination. Modern explorations of exoplanets reveal an astonishing truth. Nearly every star is likely to possess at least one planet, and many stars host entire families of worlds. Should even the most cautious estimates hold, the observable cosmos contains more planets than all the grains of sand on Earth multiplied by every atom that makes up our world. Each of these innumerable planets is a distinct experiment in the unfolding of nature's laws. Some are rocky, orbiting within temperate zones where liquid water might flow. Others are colossal gas giants dominating the outer reaches of their systems. There are icy worlds hiding vast oceans beneath frozen crusts, and scorched planets seared by unrelenting stellar fire. The diversity of these environments exceeds anything our imagination once placed in the pages of science fiction. Mathematics, when applied to such vast probabilities, leads to staggering possibilities for life beyond Earth. Even if life arises on just one planet in every million that could sustain it, the universe should overflow with biology. Civilizations may have blossomed billions of years before our sun was born, some possibly so advanced that our greatest achievements would seem rudimentary to them. Yet the immense gulfs between stars mean that most worlds remain forever isolated, separated by distances that light itself takes thousands of years to cross. This cosmic speed limit, light's finite pace, ensures that even civilizations separated by only a few thousand light years will never truly converse. Each inhabited planet evolves in its own solitude, unaware of the other flickers of intelligence scattered across the universe. The silence of the night sky is not emptiness, but the echo of isolation written into the fabric of space and time. If alien beings have ever transmitted their voices across the void, their signals would take centuries or millennia to arrive. By the time they reach us, the senders might have transformed beyond recognition or vanished altogether. Within this quiet cosmic ocean lies a humbling truth. Every human who has ever existed has lived on a single planet, orbiting a single star, one among more stars than there are grains of sand on Earth. Yet even this abundance is only the beginning. The universe we can see has boundaries, not physical edges, but limits set by light's velocity and the finite age of cosmic time. This is what astronomers call the observable universe, a vast sphere containing everything that light has had time to reveal to us. Measurements confirm that this sphere spans 93 billion light years in diameter. It marks the furthest distance from which light has reached us since the beginning of the cosmos. Beyond it lies an unreachable realm, forever hidden from observation. Understanding this boundary requires grasping both the journey of light and the expansion of space itself. The faintest rays we detect today began their voyage 13.8 billion years ago, when the universe was only 380,000 years old. But as they travelled, the universe stretched around them, expanding space, so that the galaxies that emitted that ancient light now reside 46.5 billion light years away. What we see are their distant, youthful selves, while their present forms drift far beyond our observational horizon. This reveals one of the universe's most counterintuitive truths. The most remote galaxies we observe appear as they were when the cosmos was young and compact, yet those same galaxies now exist in realms forever beyond our sight. The boundary of what we can see corresponds to the cosmic microwave background, the faint afterglow from when atoms first formed and space became transparent to light. It is, in a sense, the universe's earliest photograph, captured when it was less than 1% of its current age. But this cosmic horizon is deeply personal. Every observer, wherever they stand in the cosmos, has their own unique sphere of visibility centered on their position. Astronomers in distant galaxies gaze upon regions we will never see, just as we witness parts of the universe hidden from them. And with each passing second, our observable sphere expands by 1 light second in every direction as light from ever more distant places arrives for the first time. Over vast epochs, this growing horizon brings new galaxies into view, yet the expansion of space will ultimately outpace the reach of light, carrying those distant galaxies away faster than their light can travel. One day, they will slip permanently beyond our sight, vanishing into the eternal darkness of an ever-expanding cosmos. As the observable universe continues to expand, it will one day begin to contract, not in size, but in the reach of our cosmic vision. Galaxies that we can see today will drift beyond the cosmic horizon, vanishing forever from view. We are living in what might be called a golden age of cosmic visibility, a moment when the observable universe holds more galaxies than at any other time in its long history. Yet paradoxically, there will come a time when far fewer will remain visible as the relentless expansion separates us from our most distant cosmic neighbours. This boundary of visibility invites deep questions about the vastness that lies beyond. The universe we cannot see may be immensely larger than the region accessible to human observation. Space itself can move faster than light, a notion that seems to challenge Einstein's famous limit. But Einstein's laws govern the motion of matter and energy through space, not the stretching of space itself. The expansion of the universe is not a motion through space, but a swelling of the fabric of space-time which faces no speed restriction. During the brief, extraordinary period known as cosmic inflation, space expanded so swiftly that areas once smaller than atoms ballooned to cosmic proportions in less than 1 second. This difference between moving through space and the expansion of space leads to astonishing consequences. Galaxies near the edge of what we can observe are receding at speeds close to 3 times the speed of light, yet they are not hurtling through space so quickly. Instead, the space between us and them is stretching, carrying them away like passengers on a moving walkway. Hubble's law describes this expansion with a striking simplicity. Galaxies twice as distant recede, twice as fast, 3 times as distant, 3 times as fast. Beyond a distance of about 14 billion light years, recession speeds surpass that of light itself. The discovery that this expansion is accelerating earned the Nobel Prize in Physics in the year 2011, after astronomers studying distant supernovae found that the rate of expansion is increasing, not slowing, as once believed. Dark energy, which makes up 68% of the universe, is the mysterious force driving this acceleration, overpowering gravity on the largest scales. Current observations suggest that space doubles in size roughly every 10 billion years. Though this may sound gradual across the immense cosmic distances, it results in staggering velocities. Over time, this expansion will push most galaxies beyond our sight. In about 2 trillion years, only those in our local group will remain visible, leaving future astronomers with a dark, almost empty sky. Theorists predict that if this acceleration continues unchecked, it might one day tear apart everything: galaxies, stars, planets, even atoms, in a dramatic finale known as the Big Rip, some 22 billion years from now. Yet in the present, this accelerating expansion is both a challenge and a gift. It allows our telescopes to peer deep into space and time, to witness the universe as it once was, when young galaxies burned brightly and stars formed at extraordinary rates. Each improvement in our instruments takes us further back, revealing earlier moments in cosmic history. But even as we look deeper, most of the universe drifts forever beyond our reach. The unseen regions may stretch infinitely in every direction. At the edge of what we can observe lies a faint wall of ancient light, the cosmic microwave background. This glow is the oldest light in existence, emitted when the first atoms formed and space became transparent about 13.8 billion years ago. Before that time, during a period known as recombination, the universe was so hot and dense that atoms could not exist. Protons and electrons moved freely in a glowing plasma, scattering light in every direction. The cosmos was opaque, like being inside a radiant fog through which no light could travel far. Then, as the universe expanded and cooled below 3000 degrees, those protons and electrons combined to form hydrogen atoms. In that instant, light was released to travel freely for the first time, light that has journeyed across the ages to reach us today, carrying with it the story of our cosmic origins. In a single breathtaking moment, the universe became transparent, releasing a sea of radiation that still journeys across space to reach us today. We can observe this ancient light arriving uniformly from every direction, its temperature differing by no more than a few millionths of a degree. These minute variations are the quantum echoes of the universe's earliest moments, magnified by expansion into the first seeds of galaxies. The cosmic microwave background is in essence our universe's childhood portrait. We see it as it was when the cosmos was only 380,000 years old compared to its present age of 13.8 billion years. The delicate patterns imprinted in this light tell the story of when the first atoms formed and structure began to emerge from an almost perfectly smooth universe. Yet this ancient glow is also a boundary, an electromagnetic horizon beyond which no telescope can peer, for light simply did not exist in visible form before that time. Everything earlier than this moment is hidden behind a wall of radiation, accessible only through the faint signatures of gravitational waves or neutrinos. The cosmic microwave background envelops our planet like the inner surface of an immense sphere centered precisely on Earth, every point of which lies 46.5 billion light years away, the farthest distance light has traveled since the universe first became transparent. But this horizon is not static. It expands constantly as the universe itself stretches, pushing the source of that radiation ever farther away. As the cosmos grows, the radiation becomes cooler and dimmer, its wavelengths elongated into increasingly feeble whispers. In the distant future, this glow will fade entirely, slipping beyond the reach of any conceivable instrument. When that happens, even this most ancient trace will vanish, erasing the last visible edge of our observable universe. Yet the mystery deepens beyond that frontier. The universe before this time undoubtedly existed, but what it was like remains largely a matter of theory. Whatever lies beyond the cosmic microwave background may be far greater than anything we can see, perhaps unimaginably so. It stretches back to epochs when temperatures soared above those in stellar cores, and outward to distances that could extend infinitely. Theoretical physics offers us a fleeting glimpse into these early conditions. During the first 380,000 years, temperatures were so extreme that atoms could not form. Matter existed as a brilliant plasma, where nuclei and electrons were torn apart. The entire cosmos shone more brightly than any star's surface. Even earlier, in the first 3 minutes after the Big Bang, the universe itself became a vast nuclear furnace, forging hydrogen and helium that still fill the cosmos today. At that time, the universe was smaller than our solar system, yet contained everything we can now observe. The first second of existence remained shrouded in uncertainty. Theoretical models suggest that as the universe cooled, the fundamental forces of nature, gravity, the strong nuclear force, and the electromagnetic and weak forces split apart from a single unified state. Observations also reveal that the universe extends far beyond the limits of what we can see. The extraordinary flatness and smoothness of space suggests that during its first instant, the universe underwent a phase of astonishing inflation, expanding faster than light itself. This inflation stretched quantum fluctuations to cosmic scales, creating a universe vastly larger than the small region we observe today. If this theory holds true, then our observable universe is only an infinitesimal fraction of the total cosmic expanse, a region once smaller than a proton, before inflation magnified it by a factor exceeding 10 to the 26th power. Yet even this colossal expansion is but a bubble within a still greater cosmic sea. In that broader universe, other regions may have evolved under entirely different conditions. Physical constants could vary. Electrons might possess different masses. Light could travel at alternate speeds. Gravity might pull with unfamiliar strength. Such variations would create realms where stars form differently, where chemistry follows unfamiliar patterns, and where life itself might arise through processes beyond imagination. Each of these domains could be a separate experiment in the laws of nature, isolated from one another by an expansion too vast ever to bridge. Some theoretical models propose that cosmic inflation continues endlessly beyond the boundaries of what we can see. New space continuously emerges in this eternal expansion, forming an infinite collection of universe-sized bubbles within a vast and growing cosmic tapestry. It means that our observable universe, with its 2 trillion galaxies and more stars than all the grains of sand on Earth, may be nothing more than a single chamber in an infinite cosmic mansion. The true scale of existence might extend beyond anything the human mind can truly comprehend. Statistical studies suggest that the portion we can observe could represent less than 1% of the total cosmic volume. Bayesian mathematical models imply that the real universe may stretch at least 250 times farther than the cosmic horizon we can detect, revealing a hidden cosmos far larger than anything humanity will ever witness. This conclusion comes from examining the curvature of space across the largest observable distances. If the universe was smaller than what we can see, space would display a detectable curve like the surface of a sphere. Yet observations of the cosmic microwave background show that space is astonishingly flat over billions of light years. Such flatness indicates a universe extending far beyond our observational reach. The region we see is only a tiny patch of an immense structure so vast that its curvature remains imperceptible across the entire span of our visible cosmos. It is much like standing on the surface of Earth, where the horizon seems flat only because our planet's size dwarfs the distance we can perceive. Conservative calculations based on this cosmic flatness estimate that the universe measures at least 7 trillion light-years across. This would make it roughly 75 times larger than our observable universe. For every galaxy within our view, there could be 5,000 more beyond it, and even that may be a modest guess. Eternal inflation theory suggests that new space keeps forming through quantum events, giving birth to countless observable universe-sized regions within an ever-expanding whole. Each region holds its own galaxies, stars and planets, isolated from the rest by a rate of expansion faster than light itself could ever traverse. Such a hidden universe challenges our sense of cosmic uniqueness. If the cosmos stretches far beyond what we can see, then conditions like ours must repeat endlessly throughout the greater structure. Somewhere in that vastness, there might be planets indistinguishable from Earth. Civilizations like ours could emerge around familiar stars. In an infinite universe, mathematics tells us that every possible arrangement of matter must exist somewhere, including perfect replicas of our own observable universe repeating endlessly across infinite space. Yet this immense hidden realm will forever lie beyond human exploration. Even at the speed of light, no traveler could reach those distant regions. The space itself expands faster than light can move. The hidden universe remains something we can imagine and calculate, but never directly experience. Recent measurements of cosmic microwave background polarization give subtle clues about this larger structure. Patterns in the ancient light imply that our observable universe was once linked to neighboring regions during the earliest moments of inflation, leaving delicate traces that modern instruments can now detect. Realizing that our visible universe forms just a minuscule fraction of the whole reshapes our understanding of existence. Every star, every galaxy, every conceivable civilization within our cosmic horizon occupies less than 1% of everything that exists. The remaining 99% lies forever beyond our reach. And through it all, something unseen is driving the cosmos apart. Dark energy, making up 68% of the universe, fuels an expansion so powerful that it overcomes gravity itself across immense distances. This invisible force propels galaxies away from one another at ever-increasing speeds. The discovery of cosmic acceleration astonished astronomers who once expected gravity to gradually slow the universe's expansion. In 1998, two independent research teams studying distant supernovae found the opposite expansion was speeding up. Their revelation earned the 2011 Nobel Prize in Physics and transformed our understanding of cosmic evolution. Dark energy behaves unlike any known substance. While ordinary matter thins out as space expands, dark energy retains a constant density. As the universe grows, its influence becomes stronger. At current rates, space doubles in size every 10 billion years. That may sound gentle, yet with each doubling of space, dark energy's repulsive effect also doubles, driving an exponential acceleration that will eventually overpower all other forces. Observations confirm that dark energy now dominates cosmic motion at scales exceeding several 100 million light-years. Within smaller distances, gravity can still bind matter together. But beyond that, dark energy prevails, pushing galaxies apart despite their mutual attraction. This endless contest between gravity and expansion defines the ultimate destiny of every galaxy we can see. Galaxies within our local group remain locked together by gravity, resisting the pull of cosmic expansion. Yet across the vast reaches of space, galaxies in faraway clusters are being swept away by dark energy, accelerating so swiftly that one day their recession speed will surpass that of light itself. In roughly 2 trillion years, most of our cosmic neighbors will slip beyond the limits of what we can ever observe. The true essence of dark energy remains one of the most profound enigmas in modern physics. Many physicists propose that it may be the energy of the vacuum itself, born from quantum fluctuations within empty space. Others suggest that dark energy is not constant at all, but changes with time, or that gravity behaves differently when stretched across immense cosmic distances. Some calculations even imply that the acceleration could one day grow so extreme that it overcomes the nuclear forces binding atomic nuclei. This hypothetical future, known as the Big Rip, would see galaxies torn apart, star systems disintegrated, and atoms themselves shredded about 22 billion years from now. Yet dark energy also grants us a window into the deep past of the cosmos. Its accelerating expansion allows astronomers to look further back in time by observing galaxies whose retreating motion approaches the speed of light. Through these observations, we glimpse epochs when stars were forming at rates far greater than today. Measurements of dark energy serve as tests of Einstein's general theory of relativity across the largest imaginable scales. Each refined observation of cosmic acceleration helps reveal whether gravity follows Einstein's description or diverges at the universe's greatest distances. The discovery of dark energy transformed our understanding of what the universe is made of. The cosmos we now know is dominated by things we cannot see. Together, dark matter and dark energy constitute about 95% of its total content, leaving ordinary matter as only 5% of reality. Most of the galaxies we see tonight will vanish from view within the next 2 trillion years. Dark energy will carry them beyond our observable horizon, leaving future astronomers with a night sky nearly empty, containing only the galaxies that belong to our local group. That isolation has already begun. Galaxies lying beyond 14 billion light-years are now receding faster than light due to the continuing expansion of space itself. The light they emitted can never reach us, because the very fabric of space expands more rapidly than the photons can traverse it. We see them today only because their light began its journey when the universe was smaller. Simulations trace this unfolding loneliness in about 50 billion years. Even the Virgo cluster will vanish beyond our cosmic horizon. The farthest galaxies now visible will fade as their light becomes stretched into undetectable wavelengths. In 100 billion years, only the galaxies within our local group will remain visible. Yet, even this small community will change. The Milky Way and Andromeda, now on a slow collision course, will merge in roughly 5 billion years. Smaller galaxies will be drawn in or broken apart during this grand encounter, reducing the number of distinct systems within our cosmic neighborhood. Astronomers living in the future merged galaxy, sometimes called Milky, will gaze into a night sky devoid of external galaxies. Only the faint glow of the cosmic microwave background will remain, and even that will fade as expansion stretches its wavelengths beyond detection. Such isolation carries a sobering thought. Future scientists may have no evidence that other galaxies ever existed. The cosmic history we can trace today will be erased from the record of observation. The Big Bang itself might remain undiscovered because its clues will have drifted forever out of reach. Still, current evidence hints that acceleration could continue to increase. If the density of dark energy grows, the expansion might someday overwhelm even the gravity that holds galaxies together. Stars could be torn from their cores, planetary systems scattered, and ultimately the atomic bonds themselves broken apart. This big rip would mark the final victory of dark energy over every other force in nature, occurring around 22 billion years from now. Should the acceleration continue to rise, the universe would not fade gently into a cold stillness, but end in a catastrophic tearing of all structure. Yet other models offer a calmer future where dark energy stays constant or slowly diminishes as cosmic time unfolds. These scenarios could avert the big rip, even as distant galaxies drift forever beyond our capacity to observe them. The revelation that the cosmos is accelerating transformed our comprehension of its ultimate destiny. Rather than collapsing inward in a great crunch, the universe now appears fated to expand endlessly, growing ever more solitary and vast. We exist in a rare era, a golden window of cosmic clarity that will never come again. Earth rests precisely at the center of what we can see. It sounds as though humanity has been restored to a privileged place in the cosmos, echoing ancient beliefs that placed our world at the heart of creation. Yet, our centrality arises not from cosmic purpose, but from the fundamental rules of light and time. Every conscious observer sits at the heart of their own observable cosmos. The observable universe is defined by the sphere from which light has had enough time to reach that observer since the dawn of cosmic history. Each of us occupies the center of this personal horizon, a luminous boundary shaped by the limits of light's travel through expanding space. Astronomers on distant worlds see their own unique universes, overlapping ours, in some places extending into unseen regions in others. To them, they stand at the center of all that can be known, while our planet lingers near the edge of their horizon. This perspective emerges from the simple yet profound fact that light moves at a finite speed, and the cosmos itself has a finite age. Light from the most distant realms takes billions of years to arrive, creating an invisible edge beyond which no information can ever pass. This edge forms a perfect sphere around each observer because light radiates equally in all directions. In our case, that cosmic horizon lies 46.5 billion light years away, stretched by the expansion of space as the photons began their journey in the aftermath of the Big Bang. But our vantage point, while central in geometry, is limited in truth. We can glimpse only a minute fraction of the universe. Most of reality will remain forever unseen. Being at the center of our visible domain grants us no special access to the workings of the cosmos, no secret key to its hidden laws. The boundary of what we can see shifts constantly as ancient light from more distant regions reaches us for the very first time. Our horizon expands by 1 light second every second, gradually unveiling new frontiers. Yet, as this happens, cosmic expansion sweeps other domains forever beyond sight. The observable universe is not a fixed structure, but a moving window through both space and time. We see galaxies as they once were billions of years in the past, while nearer stars show us more recent chapters of cosmic history. Each glance outward is a step backward through time. This central perspective also defines what physics we can ever test. The laws of nature must be inferred from the slender slice of the cosmos within our horizon. Beyond that boundary, the fabric of reality itself could differ, governed by constants or forces we will never touch. The cosmic microwave background marks the farthest surface from which light has travelled freely, a glowing relic surrounding us on all sides, the outermost wall of sight itself. Beyond that ancient radiance lies a universe we can imagine but never observe. Our position at the heart of the visible cosmos carries no deeper meaning, only the quiet accident of where and when we exist. The region known as the Hubble volume defines the maximum sphere of influence that Earth could, in principle, ever reach. That sphere stretches roughly 14 billion light-years in radius, encompassing all space that could still be touched by a signal from our world before expansion isolates it forever. Within this volume, space recedes at less than the speed of light, allowing signals to one day catch up. Beyond it, expansion outpaces any form of communication. No signal, no matter how powerful, could bridge that growing gulf. Calculations confirm that radio waves sent from Earth today could in theory reach any galaxy within this Hubble domain, though their journey would last billions of years and their energy would fade almost to nothing. And as dark energy continues to accelerate cosmic expansion, even this reachable sphere is slowly, inexorably shrinking. Galaxies that now drift within Earth's sphere of influence are slipping beyond the Hubble distance ever more swiftly. Every single day, cosmic regions vast enough to hold millions of Earth-sized worlds pass irreversibly beyond the reach of any physical influence we might exert. Our cosmic neighborhood is in effect shrinking, a silent countdown for intergalactic communication. Any message humanity hopes to send to those remote galaxies must depart before they cross that critical threshold. Once they do, the accelerating expansion of space ensures that no signal, no matter how powerful or enduring, will ever bridge the growing divide. The same principle governs what we can receive. Light from galaxies already beyond the Hubble distance will never arrive, for the very fabric of space stretches faster than light can travel. We exist, therefore, in profound isolation from most of the cosmos. Current measurements suggest that the Hubble sphere encloses roughly 10,000 times fewer galaxies than the entire observable universe. Many of the luminous islands we gaze upon in our telescopes already lie outside our realm of influence. We can witness their ancient light, but no message, no gravity, no force of nature can ever link us. The Hubble volume is not just a communications boundary, it defines the ultimate extent of Earth's gravitational influence. Beyond that distance, cosmic expansion overwhelms the pull of any mass, no matter how great. This separation means that almost all matter visible in the cosmos will never interact with Earth in any physical sense. The galaxies that shimmer beyond our reach might as well belong to entirely distinct universes, forever cut off from any causal connection with us. Even if advanced civilizations within our own galaxy join forces to send immensely powerful transmissions toward those distant realms, they would still confront the same immutable barrier space itself, expanding faster than any signal can travel. The Hubble sphere thus delineates not only the edge of our influence, but also the limits of our potential role in the universe's grand evolution. Beyond this cosmic boundary, the universe continues its story, utterly unaffected by anything that happens here. And yet beyond our horizon there may lie an infinity of parallel universes, each one a separate bubble of reality where countless variations of history unfold. This idea arises naturally from the theories of cosmic inflation and quantum mechanics. Our observable universe may be just one small pocket within an infinite froth of space, where new regions continuously form through quantum fluctuations in the vacuum. Each fluctuation spawns a new expanding bubble, its own universe, with its own physical laws and distinct patterns of matter and energy. If eternal inflation is correct, then every possible quantum outcome is realized somewhere in this boundless multiverse. There exist alternate Earths where evolution took different turns, worlds where dinosaurs never vanished, or where civilizations have advanced far beyond our own. The mathematics of infinity leads to even stranger possibilities. In an infinite cosmos, every arrangement of atoms must repeat endlessly. Somewhere there are exact duplicates of our universe, including perfect copies of Earth and every human being upon it, replicated an infinite number of times. Yet these parallel realms remain unreachable. The expansion between distinct inflationary bubbles exceeds the speed of light by incomprehensible margins, making any travel or communication forever impossible. Each bubble universe evolves in perfect isolation, a cosmic island unto itself. Some interpretations of quantum theory go further, proposing that with every quantum decision, the universe branches anew, creating endless parallel timelines where every conceivable version of reality unfolds simultaneously, each as real and complete as our own. These quantum parallel worlds may inhabit higher dimensions that touch our three-dimensional reality only at the smallest quantum levels. Modern physics suggests that what we experience as ordinary space could be a lower dimensional sheet embedded within greater multidimensional frameworks known as brains. According to string theory, multiple brain universes might drift through the same higher dimensional expanse, sometimes colliding to trigger what we perceive as the birth of universes, the Big Bang events. Our cosmos could be just one brain among countless others floating through unseen dimensions. Yet the notion of parallel universes remains speculative because it lies beyond the reach of direct experimental confirmation. Support for these ideas arises mostly from mathematical consistency and theoretical coherence rather than from empirical proof. However, patterns in the cosmic microwave background may offer faint clues. Some theoretical models predict that when bubble universes collide, they leave subtle circular imprints within the cosmic radiation that surrounds us. Advanced computational methods now comb through that ancient light, searching for those traces of contact. A few intriguing signals have been found, though scientists still debate what they truly mean. The confirmation of such worlds would revolutionize our understanding of existence itself. Every conceivable version of reality could be present somewhere within the infinite multiverse. The universe we can observe, home to about 2 trillion galaxies and more stars than there are grains of sand on Earth, might be only a tiny fraction of all that exists. In fact, theoretical physics suggests that our entire observable cosmos, stretching 93 billion light-years across and containing 2 trillion galaxies, could be smaller than a subatomic particle within a grander cosmic architecture. This breathtaking idea arises from models proposing endless hierarchies of structure far beyond the limits of human perception. According to string theory and quantum gravity, space-time itself may be granular, composed of discrete units smaller than any scale we can currently measure. If space truly consists of quantum pixels, then even our vast universe might be made up of a finite number of these fundamental units of space-time. Yet infinity allows for boundless complexity within any limited region. Mathematics suggests that infinite quantities of information might be stored within arbitrarily small pockets of space-time through fractal or higher dimensional compression. This implies that our visible universe might just be one layer within an infinite nesting of realities. Inside our observable cosmos, there could exist entire universes of their own, while our universe might in turn be just one element within vastly larger realms. Advanced civilizations might one day reach technologies capable of interacting with information encoded at the quantum scale. Theoretical ideas suggest that unimaginable computational power could be concentrated within microscopic regions through quantum information processing that harnesses the fabric of space-time itself. But the infinite hierarchy extends beyond mere scaling. Each level might follow its own distinct physical laws, or even wholly different mathematical rules. The principles that govern our universe could fail completely at higher levels of the hierarchy. Some models even propose that consciousness might span multiple levels simultaneously. Human awareness could be a faint echo within cosmic minds whose thoughts endure for millions of years and whose perceptions stretch across galaxies. Conversely, within our own brains, patterns of neural activity might host entire conscious entities living their lifetimes within the span of a single human thought. Each form of consciousness might remain unaware of the others, though all share the same physical foundation. The infinite hierarchy may reach into mathematics itself. Our physical universe might be one expression within an infinite mathematical library, containing every possible logical system and geometric configuration. Within this mathematical multiverse would exist realms shaped by alien forms of logic, unfamiliar geometries, and differing numbers of dimensions. Perhaps physical existence emerges from mathematics rather than the other way around. Advances in computational science reveal that simple mathematical rules can produce infinite complexity through recursive behavior. The Mandelbrot set and cellular automata show how modest equations can generate patterns of limitless detail at every level of magnification. If reality itself follows such rules, then all the complexity we see in our cosmic environment could be just the outer layer of an infinitely deep structure, extending inward and outward from our human perspective. The realization of infinite hierarchies would redefine human meaning, making us simultaneously infinitesimal and boundless. We might exist as microscopic elements within immense cosmic networks, while within us could reside entire universes. Across every scale of being, new forms of order and awareness might flourish far beyond the reach of present human understanding. Imagine compressing our entire observable universe until it becomes smaller than an atom within a vaster cosmic whole. This thought experiment shows just how small our cosmic neighborhood might be when set against the true scale of existence that stretches beyond our most distant observational frontier. An atom measures about 110 billionth of a meter across. If we were to shrink our observable universe, which spans 93 billion light years, down to the size of an atom, then the greater cosmos containing it would extend across distances so vast that the human mind can scarcely comprehend them. The ratio between our universe and this imagined larger structure would exceed that between an atom and the totality of our observable universe itself. Some theoretical models even propose that this relationship might describe reality as it truly is. The concept of eternal inflation suggests the creation of endless realms of space, each containing countless observable universes. To an observer existing at the level of the infinite structure that holds them all, each universe would appear microscopically small. Yet this scaling can continue without end. If there are infinite layers of structure, then the vast framework that contains our universe might itself be smaller than an atom within a still greater cosmos. This recursive scaling could, in principle, continue forever, rendering our observable universe infinitely tiny compared to the ultimate reality. Modern physics proposes that it is not physical size, but information that determines significance. Our observable universe carries about 10 to the power of 120 bits of information encoded in the positions and properties of every particle that fills space. Perhaps this information is the truest measure of our cosmic worth. Even if our universe were as small as an atom, when viewed from a higher level of existence, it might contain unique information patterns, arrangements so intricate that they hold meaning for cosmic minds, far beyond our comprehension. Some models even suggest that consciousness could exist across multiple scales at once. Enormous cosmic intelligences might think thoughts vast enough to encompass our entire observable universe, while remaining blind to the details of human thought. Conversely, the quantum events within our brains might themselves host sentient entities, living entire lifetimes within what we perceive as a single flicker of neural activity. Each scale of consciousness might experience its own flow of time, all woven together within the same underlying reality. If our universe exists as a subatomic feature of some greater structure, then the notion of importance itself must be re-examined. Every human triumph, every supernova, every galactic collision could be nothing more than microscopic ripples within processes far larger than we can imagine. Yet this relationship also suggests something profound, that complexity and wonder might exist at every scale. If our universe can be compressed to the size of an atom while retaining its full informational richness, then perhaps each atom in our world conceals universes of its own. In this fractal architecture, complexity would have neither upper nor lower limit. Zooming outward or inward would endlessly reveal new layers of organization. Quantum mechanics tells us that even empty space teems with virtual particles flickering into and out of being at subatomic scales. These fluctuations might be faint reflections of deeper cosmic processes unfolding within the very fabric of space-time. It could be that our entire universe is merely foam on the surface of an infinite ocean of existence. As you hear these words, remember, you are on one planet, orbiting one star in one galaxy, among 2 trillion others scattered through the observable universe, a universe that may itself be smaller than an atom compared to ultimate reality. The scale of this vision reframes everything we assume about meaning and purpose. Earth measures roughly 25,000 meters around a tiny rock spinning through space at 67,000 miles per hour around a star that converts 4 million tons of matter into energy every second. Our sun is utterly ordinary, one among 400 billion in the Milky Way. The Milky Way itself stretches 100,000 light years across and contains enough starlight to power quadrillions of civilizations. And yet it is but a single grain of sand on a cosmic shore where there are more galaxies than there are grains of sand on every beach on Earth. Each of those 2 trillion galaxies shelters billions of stars, and many of those stars host planets where life may thrive. Conservative estimates suggest that hundreds of billions of Earth-like worlds exist within the observable universe. Some may have birthed civilizations millions of years before our own began, and still the region we can see might be less than 1% of all that is. Beyond our horizon may lie a universe that stretches infinitely, filled with unending galaxies, stars, worlds, and perhaps uncountable minds gazing back into the depths of existence. Parallel universes may exist, where alternate versions of reality unfold, each shaped by different quantum outcomes. Perhaps there are infinite layers of cosmic hierarchy, with our entire observable universe merely a microscopic fragment within structures so vast they defy comprehension. From such a cosmic viewpoint, human life seems both vanishingly small and deeply significant at once. We are fleeting arrangements of organized matter that somehow develop the extraordinary capacity to reflect upon the cosmos itself, reaching far beyond our evolutionary beginnings. From humble chemical reactions on a tiny planet, life emerged. From there, we built tools to trace structures stretching across billions of light years. Our ancestors once hunted beneath the African sun, and yet now we have charted the vast architecture of the universe and captured the whispers of space-time itself, gravitational waves born from the collisions of black holes. The same cosmic mechanisms that forged galaxies, stars, and planets also crafted the intricate chemistry that gave rise to life and consciousness. We are quite literally made of star material elements formed in the nuclear hearts of stars and cast into space by their explosive death. Every atom in your body except hydrogen was born within a star that lived and perished long before the birth of our solar system. The calcium in your bones, the iron in your blood, the oxygen you breathe, all trace their origins to stellar furnaces burning billions of years ago in distant corners of the galaxy. This connection ties humanity to the evolution of the universe itself across space and time. We are the universe awakening matter that has become aware, contemplating its own beginnings. Though we occupy a mere speck in an endless cosmos, we have uncovered truths that hold across unimaginable scales. We have glimpsed the immensity of existence, and in doing so discovered something profound about ourselves. The universe is not only stranger than we imagine, it is stranger than we can imagine. And we are here, conscious and curious, to witness it.